Welcome viewers. In this video we'll see the energy stored in capacitor, energy density of the capacitor and the problem. First we'll see energy stored in capacitor. So the parallel plate capacitor is shown in diagram. At one plate positive charge is available, another plate negative charge is available. The voltage is applied between the two plates. Right? The voltage is applied. What will happen? The voltage across the capacitor is V. The voltage will be developed. In the closed loop, the voltage across the capacitor will oppose the supply voltage. So we are giving the supply voltage V so that the voltage is developed across the plate. That voltage will oppose the supply voltage. Right? The voltage across the capacitor parallel plate will oppose the supply voltage. The work done by the source against the opposition of V is converted into energy. So there is a opposition between parallel plate voltage and supply voltage. So that will be now converted into energy. Right? So we know that potential is the work done per charge. So what is the potential? V equal to dW divided by dQ. The potential equal to work done per unit charge. From that dW equal to V into Q. Cross multiply these two. So the dW equal to V into dQ. But we know that Q equal to CV. From that V equal to Q by C. We will replace this V as Q by C. So dW equal to Q by C into dQ. So this work done is due to only small charge. So by integrating on both the side, we will get the total charge. dW equal to Q dQ divided by C. So we have one parallel plate capacitor, voltage is applied. Then the voltage will be developed across the parallel plate. That voltage will oppose the supply voltage. That is now converted into energy. That is nothing but dW divided by dQ. Work done by charge. So after simplification we got this value. This is only small charge and small work done. By integrating on both the sides with a limit, we will get the total work done, total energy stored. If the capacitor is initially uncharged and the process of charging continue until the charge Q is reached. That is, the capacitor is charged from 0 to Q, initially uncharged, and then it is charged to Q. Then the total work done will be, so we can integrate this both the side with a limit 0 to Q, because the capacitor is charging from 0 to Q. Now see this, integral dW equal to integral 0 to Q, Q dQ divided by C. Now it is integrated on both the side, the limit is applied. So integral dW equal to W. 1 by C is constant, so integral 0 to Q, Q into dQ. So W equal to 1 by C, the integral Q is nothing but Q square by 2. We need to substitute the limit 0 to Q. So what will happen? 1 by C into Q square by 2. So that Q square divided by 2C. The energy stored in the capacitor is Q square divided by 2C. By substituting this limit, Q is replaced, small q is replaced by capital Q. So that Q square divided by 2C. You take this equation number 1. This is one formula. Energy stored in capacitor, one formula. Q square divided by 2C. We will see another two formulas. We know that Q equal to CV. Now we are going to substitute Q equal to CV in the equation number 1. So that what is that? W equal to Q square divided by 2C. That is, Q square means C square V square divided by 2C. Right? This Q square is now replaced by C square and V square. So 1C got cancelled. So what we have? C V square divided by 2. So that is nothing but half CV square. Energy stored in capacitor, another formula is half CV square. This is a very standard formula. Half into capacitance plus voltage square, half CV square. This is second form is available. Now we'll go to the third form. Same thing, Q equal to CV. From that, C equal to Q by V. We are going to substitute in the equation 1 C. We are going to replace the C value by Q by V. Here we replace the Q value by CV. This Q is replaced here. In this third form, the C is replaced by QV. Right. So what we have, Q square divided by 2C. So that Q square divided by 2 into C is nothing but Q by V. So 1 Q square is there, here Q is there, 1 Q got cancelled. This V is available in the denominator, it will go to numerator. So QV divided by 2, that is half QV. That is the third form. Right. So we have 3 different formula available. According to the data, we can use any of this formula for the energy stored in capacitor. Q square divided by 2C or half CV square or half QV. 3 different formula available. Based on the data, we can use either any one of this formula. Now we'll see the energy density. What is energy density? Energy density is defined as the energy stored per unit volume. So always density mean either length, area or volume we are referring. Here we are referring the volume. Energy stored per unit volume is nothing but energy density. Right. So the energy stored in the capacitor. Just now we discussed the energy stored in capacitor. 3 different form available. We consider the one form, half CV square. We will take this form, half CV square. So this energy stored by volume is nothing but energy density. So first we started with the expression half CV square. But we know that the capacitance is nothing but A epsilon by D. Area into epsilon divided by distance. Right. Now substitute the C, replace this C by this value, A epsilon by D. So half A epsilon by D into V square. For in order to get the volume, multiply and divide by the term length. So it will not, the originality will not affect. Multiply and divide by the term length. Right. Now we rewrite this 1 by 2 epsilon V square. This epsilon V square. Right. A into L divided by D into L. Right. So this L is written here. This L is multiplied with A. Right. So half epsilon V square divided by DL into A into L. Right. This L is available here. This L is available with multiplication of area. What is area into length? Area into length is nothing but volume. Area means 2 parameters, length and breadth, or length and height, or breadth and height. So breadth, height into length, 3 parameters. This is 2 parameter, this is third parameter. If 3 parameter if you multiply, that is volume. So what we have, energy stored equal to half epsilon V square divided by DL into volume. Right. Now bring this term volume in the denominator. Energy stored is denominator. So energy stored by volume equal to half epsilon V square divided by DL. Right. This volume is brought into denominator of left hand side. So what is this energy stored by volume? Energy stored by volume is nothing but energy density. That is half epsilon V square divided by DL. Right. Now we got the expression for energy density, that is half epsilon V square divided by DL. So based on this energy stored and energy density, we will see one problem. So we have parallel plate capacitor with 2 parallel square plate of area 50 centimeter into 50 centimeter. Right. The area is 50 centimeter into 50 centimeter, that is 50 into 50 10 to the power minus 4 meter square. By converting centimeter to meter, we need to multiply 10 to the power minus 2. Here 2 terms available. So that 10 to the power minus 4 meter square. Right. So the area is given. Separated at a distance 1 millimeter. The distance between the plate is 1 millimeter. That is 1 into 10 to the power minus 3 meter. It is charged with 500 voltage. The voltage will be 500. Then what we need to find? Work done in separating the plate from 1 millimeter to 3 millimeter. right? The distance between the plate is separated from 1 millimeter to 3 millimeter. So that we'll take D1 as 1 millimeter, D2 as 3 millimeter, right? So 3 into 10 to the power minus 3. The epsilon naught is constant, 8.854 into 10 to the power minus 12. Then epsilon r equal to 1. We consider air medium. What we need to find? Work done. What is work done? Half CV square. The V is already available, but C value is not available. How will you find the C value? By using this data we can find. We will take this C1 and C2. If it is 1 millimeter, C1. If it is 3 millimeter, C2. So that is available here, C1 and C2. From C1 and C2 we will find the work done, WD1 and WD2. From that we can find the net work done, right? So we have the distance is 1 millimeter to 3 millimeter. So first we consider 1 millimeter. We can calculate C1 value. Then we will consider 3 millimeter. We can calculate C2 value, right? So that C1, C2 using 1 millimeter. This will be using 3 millimeter. So A epsilon naught epsilon r divided by D1, 1 millimeter. So area is 50 into 50 10 to the power minus 4. Epsilon naught is 8.854 into 10 to the power minus 12 divided by this distance, 1 into 10 to the power minus 3. So C1 equal to 2.21 into 10 to the power minus 9 farad. By simplifying this we got this value. So when the distance between the plate is 1 millimeter, this is the capacitance value. When it is 3 millimeter, it will be C2. A epsilon naught epsilon r divided by D2. The area is 50 into 50 10 to the power minus 4. Epsilon naught is 8.854 into 10 to the power minus 12. The D2 value is now 3 millimeter. 3 into 10 to the power minus 3. By simplifying what we got, 7.37 into 10 to the power minus 10 farad. Right, now we got the C1 value and C2 value. By using this we can find what is the work done for C1, what is the work done for C2. The difference between that two will be the net work done, right? So I will find this work done now. So the work done WD1 equal to half C1 V square. Voltage is common, only C1 is there. So half into C1 we calculated, 2.21 into 10 to the power minus 9. The voltage is 500 voltage, 500 square. That is equal to, by simplifying this, 2.76 into 10 to the power minus 4 joule. Right? When the distance is 1 millimeter, this is the capacitance value, this is the work done. When the capacitance is C2, half C2 V square. When it is 3 millimeter, the capacitance value will be C2. For that, the work done will be half C2 V square. Half into C2 is 7.37 into 10 to the power minus 10 into 500 square. V square is 500 square. By simplifying what we got, 9.21 into 10 to the power minus 5 joules. Right? So this is the work done when it is 1 millimeter. This is the work done in 3 millimeter. Then what is the net work done? Difference between these two, WD1 minus WD2. We need to subtract these two values. So what we got, 1.83 into 10 to the power minus 4 joule. The net work done by moving the distance between the plate from 1 millimeter to 3 millimeter. This is the total work done. Net work done, 1.83 into 10 to the power minus 4 joules. So in this video we discussed the energy stored in capacitor, then followed by energy density, then one problem we discussed based on the energy density, energy stored. Welcome viewers. In this video we'll see the energy stored in inductor and energy density of the inductor. First we'll see the energy stored in inductor. Let us consider this inductor is available. It is connected with the DC supply. It is connected through switch and the ammeter. When the DC supply is given, the current will flowing through the inductor. So due to rate of change of current, EMF is induced in the inductor. See the direction, the induced EMF is opposing the supply voltage. This opposition is converted into work done, that is nothing but energy stored. The opposition of the induced EMF by the voltage source is converted into energy stored in the inductor. Right? So an inductor is available energized with the DC supply through the switch and ammeter. When the DC supply is given, the current will flowing through the inductor. Due to rate of change of current, EMF is induced in the inductor. That EMF will oppose the supply voltage. So the work done by the DC source against this opposition is converted into energy stored in the inductor. So the work done is equal to energy stored. So the details are given. Ammeter, this S is nothing but switch, V is the DC voltage source, E is the induced EMF, L is the inductor. So the description is available. When a DC voltage is applied to the coil, the current increases exponentially. Due to change in current, an EMF is induced in the inductor. The direction of induced EMF is such that it opposes the applied voltage in the closed loop. There is a opposition between induced EMF and applied voltage. So the work done by the DC source against the opposition is stored in the form of energy in the inductor or magnetic field. Right? So this work done is nothing but done by the DC source against the opposition, that is converted into energy. Right? So the induced EMF in the inductor, the induced EMF in the inductor is nothing but E equal to L di by dt. It's a normal general formula. E equal to L di by dt. Now dW is the work done to increase the current by I. What is the work done? Increasing the current from 0 to I. That is to the current di. So by law of conservation of energy, work done is equal to the energy stored. This work done is nothing but energy stored. Both are equal. Right? So this is the EMF induced. In this, the energy stored is nothing but to need to increase the current by the di value. So that the increasing the current is the energy stored, that is equal to the work done. Now we'll see what is the work done. So the energy is given as power into time. The general formula for energy is nothing but power multiplied by time. This energy is equal to the work done. Just now we discussed the work done is equal to the energy. So the energy is represented as dW, work done. This dW represents the work done by small current. By integrating, we will get the total work done. So the power is nothing but voltage into current, EMF induced into current, into time is dt. Right? This EMF induced in the inductor is L di by dt. Just now we discussed this formula, L di by dt into I into dt. So this dt got cancelled. So what we have, dW equal to Li into di. Right? So this is the work done due to the small current di. Work done, dW means small work done by the small current. So the total work done to establish the current of I can be obtained by integration. So by integrating on both the side with a limit, we can get the total work done. So integral dW equal to integral Li into di. What is the limit? The work done is nothing but increasing the current from 0 to maximum value of current I. So the limit is from 0 to I. The work done is nothing but increasing the current from 0 to I. Now we'll go for this integration. So integral dW equal to W, that is equal to, this L is constant. Only we need to integrate 0 to I into di. We need to integrate only I. So W equal to L, this integral I is nothing but I square by 2. Right? Integral of I is I square by 2. We need to substitute the limit 0 to I. So W equal to L, substitute the upper limit I square by 2 minus lower limit is 0. So that W equal to L I square by 2. So that can be written as W equal to half L I square. So that is the energy stored in the inductor. W equal to half L I square. So this I represents the energy stored in inductor, means current is increasing gradually or current is decreasing gradually. The charging, the inductor is storing the energy or discharging the energy, means current increases or decreases gradually. In case of capacitor, the work done is nothing but half CV square. The voltage in capacitor, charging and discharging, means the voltage is increasing or decreasing gradually, right? So the inductor W, energy stored, equal to half Li square. Now we'll see the energy density of the inductor. Now we'll see energy density. So the energy density is nothing but energy stored per unit volume. So the density means always we can refer either length, area or volume. Here we are referring volume, right? Density, how much density for a given volume, right? So the energy density is energy stored per unit volume. So for that, first we'll start with the energy stored. Energy stored in the inductor. Energy stored in the inductor is half Li square. Just now we discussed half Li square. In this, what is the inductor? Inductor value, general formula n pi by I. Now we'll substitute this L, replace this L with n pi by I. Therefore, energy stored equal to half Li square. L is nothing but n pi by I into I square. So one I got cancelled. So half n pi into I, right? So the energy stored is half Li square. In this, L is replaced by n pi by I. At the time one I got cancelled, we got half n pi into I. In order to get the volume, we are going to multiply and divide by the term length L, right? We are going to multiply this expression and divide by the length L, so that energy stored equal to half n pi by I into L divided by L. So while multiplying and dividing, the originality will not change. Now rewrite this 1 by 2. This n into L is written separately, n into L. Remaining pi I divided by L is rearranged, right? N into L is written here, pi I divided by L is written here. So n into L is nothing but number of turns into length, is nothing but a volume, right? So that is written as pi I divided by 2L into volume. Number of turns multiplied by length is nothing but a volume, right? So now we can see that. Now bring this volume in the denominator, this left hand side. Energy stored by volume equal to pi I divided by 2L, right? This volume is brought in the denominator. What is energy stored by volume? Is nothing but energy density. Energy stored by volume is the energy density, that is equal to pi I divided by 2L. The unit is joules per meter cube, because it is divided by volume, it is meter cube, joules per meter cube, right? So the energy stored in the inductor is nothing but pi I divided by 2L, joules per meter cube. Now we'll see the energy density of the solenoid. So the energy stored in the energy density of the solenoid, right? And this energy density is nothing but energy stored per unit volume. So first we will refer the energy stored in the inductor. Energy stored equal to half Li square. In that, what is the inductor value? The previous derivation we refer the general formula, L equal to n pi by I. Here we are referring inductor of a solenoid, right? Because we are going to find energy density of the solenoid, right? So the inductor of the solenoid is nothing but mu n square A by L, right? We need to replace this inductor expression with the inductor of a solenoid, mu n square A by L. So that energy stored equal to half Li square. L is nothing but mu n square A by L into I square, right? So in order to get the volume, here also we are going to multiply and divide by the length L, right? Multiplied and divide by the length L. So that energy stored equal to half, that is mu n square A divided by 2L into I square divided by L into L. right? We are going to multiply and divide by the term L. Now rewrite this mu n square divided by 2L into I square. A into L is written separately, right? A into L, area into length. Remaining terms are written here. Mu n square, this I square divided by 2L. Here 2L is available. L, here one more L is available. L square. A into L is rewritten. What is area into length? Area into length is nothing but volume. Area refers two parameters into one more parameter. Three parameters means it is a volume, right? Breadth into height. We can refer breadth into height in the area. Into length. Length, breadth, height means it is a volume, right? Now energy stored equal to mu n square I square divided by 2L square into volume, right? Now bring this volume in the denominator. This volume is brought into denominator. So energy stored by volume is nothing but energy density. That is mu n square I square divided by 2L square, right? This is L square. Joules per meter cube, right? So this is the expression for energy stored in the solenoid. Previous one is the energy stored in inductor in general. This is specifically for a solenoid, right? Now we'll see one problem based on the solenoid. So in this problem, a solenoid with 200 turns, the number of turns equal to 200, 3 millimeter long. The length of the solenoid is 3 millimeter, that is 300 into 10 to the power minus 3 meter, right? The millimeter is converted into meter. And 20 millimeter in diameter, right? The diameter is 20 millimeter, then radius will be 10 millimeter. That is converted into meter. 10 into 10 to the power minus 3 meter, right? The number of turns available, length is available, diameter available. From that we calculated radius. The current is 600 milliampere. 600 into 10 to the power minus 3 ampere. Milliampere means we need to multiply with 10 to the power minus 3, right? What is then? We have the constant mu naught equal to 4 pi into 10 to the power minus 7, right? What we need to calculate? We need to calculate inductance of this solenoid and energy stored in the solenoid, right? Energy stored as well as inductance value. We'll find this one by one. So the inductance of the solenoid is L equal to n square mu A by L. Inductance of a solenoid is, just now we discussed about that, n square mu A by L, right? This A is nothing but pi r square because we are having the radius available, so the area is nothing but pi r square. So n square mu pi r square divided by L. Now we'll substitute all the values. The number of turns is 200, 200 square into mu. Mu is nothing but mu naught. Mu r value is 1. So mu naught is 4 pi into 10 to the power minus 7 into pi r square. Pi into r square. R is nothing but 10 into 10 to the power minus 3 square divided by L. Length is nothing but 300 millimeter. That is 300 into 10 to the power minus 3. Now all the values are substituted. By simplifying this, what we got? 5.263 into 10 to the power minus 5. The unit is Henry. So the inductance of the solenoid is 5.263 into 10 to the power minus 5 Henry. Right? Now we'll find the energy stored in solenoid. Energy stored. What is the formula for energy stored in general? Half Li square. Right? We got the derivation half Li square. So half into L. L is nothing but just now we calculated 5.263 into 10 to the power minus 5 into I square. I is 600 milliampere. So 600 into 10 to the power minus 3 square. Right? So by simplifying this, what we got? 9.4 into 10 to the power minus 6 joule. Right? The energy stored is given in joules. So 9.4 into 10 to the power minus 6 joules, right? So now we calculated inductance of the solenoid, energy stored in the solenoid. So in this video, we discussed about energy stored in inductor or magnetic field. Then energy density of the inductor. Then energy density of the solenoid. Based on that, we discussed one problem based on the solenoid, the inductor value as well as energy stored in solenoid. Thank you.